my name is Xinchi. I'm currently a PhD student in machine learning system groups here in Cambridge. This work is done by me and Javier and other people in the groups, and it's accepted to the iClear this year. So in general, federated learning is costly in terms of both computational cost and communications cost. And by our previous research, it is found like the federated learning can be higher in energy footprint than centralized learning in many perspectives. And there are currently many different ways to address this challenge. For example, by having smaller model to reduce the on-device training and then to reduce the communication cost, or we can compress the model before updates and send to the server to reduce the communications cost, or we can do different distillation methods on the server, or we can apply different pruning models based on the compute capabilities of the clients listed as different papers. And here in our ZeroFL methods, which consists two parts. The first part is to reduce on-device training by introducing sparsity in the local training. And the second part is to reduce the uplink communications between the clients to the server by using the specific client masking method. For the on-device sparse training, we adapt the SWOT method into the training. The SWOT consists two parts. The first part is in the forward part, we partition the weights into the active and non-active sets based on the magnitude. And then in the backward part, we use the dense gradients, and then we partition the weight and the activation into the active and non-active based on the magnitudes again. And then because of these sparse dense convolutions, which can be accelerated on the spotted hardware if we have the sparsity ratios high enough. And how high is enough, it depends on the structure of the sparsities. And here in our experiment, we use unstructured sparsity. So over 90% of the sparsity ratio is required, and hence we use over 90% of the sparsity ratio in our experiment. We use the SWOT in the federated learning framework by treating each local training as one centralized sparse training. And unlike the centralized training, the federated learning have the problems with the local dataset distribution, very different from the global dataset. And then the local dataset distribution can be non-ID and then very different from client to client. As we can see from the plots here, by using the over 95% sparsities, the centralized training holds up quite well with minimal degradations in the performance. However, in the federated learning scenarios, the performance drops quite a lot if we introduce higher sparsity ratios. And then the second part is we investigate the position of the sparsified weights. So because in the forward pass only we partition the weights into the active and non-active parts, and only the active weights are used in the forward propagations in the evaluation and during the inference time. So non-active weights are not significant in the inference time. And then if we see the heat map here, the white part is the specified weight, and the color part is depends on the magnitude and the positive and the negative. So we can see like the white remains white throughout the training process, and the y-axis is the position of the weights, which means that we can send the top case weights to the server for aggregation without reducing the performance. And by only sending the top case weights, we can send in the most important information from the client to the server, and also avoid sending the noise because of the non-IDness of the local data set coming from the training process. In the experiment, we use 3 different data sets. The speech command is a keyword spotting data set, and the FedMins is the leaf federated learning specific data set partitioned by the writer's ID. For both CIFAR10 and the speech command, we use the ResNet 18 and introduce the sparsity in the CNN layers, and in the FedMins data set, we specify everything apart. We use the simple CNN models and specify everything apart from the last layer. And the models here shows that the ZeroFL, which sends only the top non-specified weight plus additional 20% of the weights to the server for aggregation, and then it outperforms the full model, which is sending all the weights from the client to the server. And there's also the table here is quite restricted. It doesn't include everything. And then in the, if we look at the paper, which shows that there's a trade-off between the communications and the performance. And if we increase the mass ratio from 0 to 0.2, the performance is generally better for the mass ratio of 0.2 than mass ratio of 0. And for the future directions of the research, because currently we are only doing the unstructured sparsities, and then more structured sparsity can be introduced and or can be explored, or we can try to explore different way of the masking method. Currently, we are only using the masking method solely based on the magnitude. And thank you very much. Here is my email address in case you have any questions in the future.
So questions for Xinchi in the audience. What's it going to take for this technique to allow people to actually train faster under federated settings?
Currently, we are only simulating the sparse training. We have not tested on the supported hardware yet, which is our next step. So after we test on the which requires the specific package of the sparsity induced hardware, which I think is our next step, and then it can be used actually on the real devices for the federated learning settings.
So do you know, is it going to be able to use some of the sparsity that like the NVIDIA cards support?
I believe so, yeah.
You believe so? Okay, cool. Great work. Thank you very much.